Good evening, everyone. Thank you for joining us on another Learn With Us workshop led by IX. Today, we will be covering the topic of quantum key distribution. The title of the presentation is Demystifying Quantum Key Distribution, led by Melchior Almans. Melchior is working with Juniper, and today, together with Melchior, we will explore how quantum key distribution works and how it can be leveraged in existing security mechanisms. Moreover, Melchior will make a brief introduction about quantum networking, what is quantum internet, and finally, what is the role that an IXP can play in this universe. So regarding the moderation, if you are willing to make any comments or questions to Melchior, you can do so as he presents, or by interrupting him, or by the end, either via the chat or by raising your hand and giving the mic, the open mic to pose the question to Melchior. So Melchior, the floor is yours. Thank you.
All right, thanks, Michalis. Yes, and I won't be monitoring the chat, but Michalis promised me he would take the honor of doing so. So if there's any questions, feel free to chime in. I am sharing my screen now. You should be able to see that. So yes, the topic of today's presentation and discussion is about how we can make quantum aspects or quantum properties applicable to networking. It is just a subsection, which is probably the most interesting use case at the moment. We'll dive into that. That is quantum key distribution. But before we do so, I think it would be good to start with some of the terminology and concepts. By the way, I am not a physicist at all. To start off, what and where could quantum be interesting for us as network operators? There's basically three fields of interests we've defined, and with we, I mean I'm part of a so-called study group or pathfinding mission in Juniper that is looking in this case into how can we leverage quantum. And we sort of came up with three areas. The first is using quantum random number generators. And a quantum random number generator, or QRNG, is basically a chip you can use in a firewall or switch or any device, and that generates randomness. And why is that interesting to us? The way we currently create randomness by using urandom, for example, is to take environmental properties of a router switch. That could be the fan spinning, could be the voltage, etc. But it turns out that it's not as random as we've hoped. And there has been many studies in that space. And by using a quantum random number generator, we can increase the level of randomness. So in other words, the source, the random source we're using to generate keys is apparently much better when doing that with using quantum aspects. The second thing is to use quantum properties to actually transport data, in this case called quantum key distribution, where we're using some of the quantum properties to generate and send keys from one side, Alice, to Bob on the other side. And that is what we will explore further down in this presentation. And the third thing is, which is an interesting field, is post-quantum cryptography. That basically means encryption protocols and encryption mechanisms that are quantum resistant. In other words, that cannot be hacked or factored by using quantum computers. So why is this interesting? I mean, AES 256, as we currently all use it in, for example, MACsec, is on itself a pretty much secure against attacks from quantum computers. The way it works, I won't go into all the specifics, but basically what you're doing is you're multiplying prime numbers to generate a key. And why these keys are so secure? Because factoring a prime number is really hard for computers as we know them, right? For x86 processors. So that part is actually quite secure. And if at one point it wouldn't be enough anymore, then we simply double the key size and we'll start using AES 512, for example. The part that is that has an issue is the way we communicate the keys between the nodes. So the asynchronic public key infrastructure. That is the part that is vulnerable to quantum attacks and quantum computers. Why? Because there is a algorithm that is called the Shor's algorithm, which is an algorithm that runs on a quantum computer and that is supposed to have much less issues with factoring prime numbers. As I mentioned, that is probably the hardest task you can give to x86. The way a quantum computer works is that it's much better at factoring these prime numbers. So at one point, if a quantum computer becomes available, then you can factor the keys, and by doing so, you have access to the data. So what we already see happening, obviously, is that large portions of data which are being sent over the internet are stored by southern governments, for example, with the idea that once they have a quantum computer available, they're able to factor the key and then retain access to the data. So that is what we're trying to solve, the way to communicate the keys between two or more parties. And to also answer the question what it is not, we are in quantum key distribution not using any quantum computers. So you won't need the whole 6K Kelvin cooling or any other really high-tech quantum computers, because currently, obviously, you cannot have a quantum computer in your office or data center yet without having all these thermal adjustments, etc. We are also not transporting anything. Many folks think with quantum that we're trying to teleport physical objects. We are not. The only thing we're doing is sending, in this case, photons from one side to the other. Using a laser, you can polarize those photons, and in the polarization, you can transmit data. We'll get to how that works. Let's say that, and the last thing is that PQC, I already mentioned, post-quantum cryptography, is not the successor of QKD. It is developing, or it's a set of security mechanisms and protocols that are quantum resistant. So let's look at some of these quantum aspects and why these are interesting. Probably the biggest difference is if you compare a so-called classical bit as we know it, that can be either 0 or 1, and a qubit, a quantum bit, is that a quantum bit can have a value of a 0 and a 1, or 1, but also can be in both states. As I said, I'm not a physicist, so really going into how this works would also take probably too much time. But by using this laser, as I mentioned, you can bring a photon into sort of a superposition. And that superposition means that it is spinning, as you can see in the right side. The only way to know if it's a 0 or 1 or anything in between is if you measure it, or in other words, if you observe it. So at that point, you will know if it's a 0 or 1. And that is why, for example, in using in a quantum random number generator, that is exactly the reason why it is so random, because you will only know what state it is in if you measure it. So it's considered to be completely random. Keep that in mind. As I mentioned, the superposition, it's a state you can put a photon in or electron. In this case, we're using photons, which we will be sending over a dark fiber or a wavelength. But basically, you are using a laser to create that superposition. In other words, it gets a sort of sinus or spin it moves into. Superposition means you can give it a certain value. So with that laser, you can polarize it into 0, 45, 90, 135, and 180 degrees polarization. And by doing so, we'll see later on, and that is what you can use to transport this key material. Then there's the aspect of quantum teleportation. And again, we're not teleporting physical objects, so we cannot teleport ourselves to anywhere in the world yet. But we're just teleporting, as I said, quantum states. So there is a mechanism that's called entanglement, where you can, if you bring two of these photons really close together, they become sort of related to each other, or at least the quantum states become similar. So if you then take them apart and you would measure one side, and that would be 0, and then the other side will always be a 0 as well, if you measure it. Why that works is the part where we would need a physicist to explain that. But this is a really interesting phenomenon. So you have two photons, bring them together, they sort of get entangled, as it's called. So they create a sort of a relationship. You take them apart, and if you measure one, the other one will have exactly the same, will give exactly the same result. So it is random what you measure, but there is a relationship that will give the other side the same result. The interesting thing is that now if someone in the middle tries to measure one of the photons, then the other side will also collapse, obviously, into that same position. But the man in the middle won't know if at what polarization the sender has sent the photon. So you can perform a man in the middle tech. You can read if it was a 0 or 1, but you won't know the polarization. So you cannot put another photon, polarize it, and put it on the fiber and send it to the other side, because you don't know the original state. We'll get to how that works. But that is one of the reasons why this is so secure, because you basically, once you start interfering or looking into the communication, the error rate will rise, obviously, as the other side will receive photons which were he receives in a different polarization than the sender. And if that error rate rises, you will then know that someone is interfering with the communication. So some of the advantages already mentioned. You cannot interfere, or you can, but then the superposition collapses. So then the outcome won't be random anymore. And especially if you compare it with the photon that was sent, then the receiving side will see different measurements, error rate rises, and you know that there's someone interfering with your connection. Also, you cannot copy qubits. That is definitely an advantage for security. The downside is that you cannot use active CWDM or DWDM to increase the distance, right? Currently, the maximum distance you can span between two QKD devices is around 120, 140 kilometers. And if you would amplify the signal in the middle using a booster or any other amplification method, the quantum state will get lost, and so it's useless again. Another advantage is it's physics over math. So instead of using an algorithm or something like TLS or any mathematical based protocols, you can obviously factor and crack those. Physics you cannot factor, right? There's no way you could, with a computer, try to factor physics. As I mentioned, scaling is on the other side definitely an issue. Currently, these are all one-to-one relationships. So if you we'll get to that in the next slide as well. There is no, let's say, quantum internet as we currently know it. It's all point-to-point connections. Decoherence is an issue. So that means the ability for the qubit or the photon to maintain that superposition over time. So you cannot really store qubits yet for longer time than a couple of seconds. I think currently they're up to maybe a minute or something. That is also an advantage because you cannot interfere with the connection, store the qubits and do the measurement later. But it's obviously also a challenge. And then there is the fidelity, that is simply said the quality of the entanglement or the qubit. At one point, if you measure, the outcome will always be the same. So the quality goes down because there's no randomness anymore. It's maybe a bit abstract, but I'm trying to give you an idea of the advantages and challenges here. So how can we sort of use this? As I already mentioned, there is no quantum internet yet. It's all basically point-to-point connections with quite a few downsides. I already mentioned you would currently need either a dedicated fiber or a wavelength without having too much in the path. You cannot have amplifiers. It cannot be an active connection, so it needs to be a wavelength you can use, but you cannot amplify it, and preferably there's not too much patches in between either. If you have dark fiber, you can reach around 120-ish kilometers, depends a little bit on which vendor you're using. If you have too many patches in between, or if you're using CWDM or DWDM, the distance goes down dramatically. So think about 60 kilometers, for example. There is a solution to that, that is using free space solutions, or in other words, based on satellites. That is where you would have a satellite and two base stations that receive photons from the satellite. The downsides, obviously, you need a satellite. There's companies where you can rent space or capacity on their satellite, but you would also need, obviously, satellite receivers or dishes on the rooftop of your data center or office. But obviously you can span much larger distances by using satellite. In this case, we're discussing a solution that is using physical telecom fibers. So to give you an idea about, as I said, quantum networking, it's basically all point-to-point. There is work going on in the standards bodies, IETF, but also within the more of the university and education world. One of the things the physicists are looking into is a so-called entanglement swap. That is where two parties form an entanglement with one, let's say, trusted man in the middle. That would mean you have two of these photons entangled, and then the man in the middle will do an entanglement swap. Again, trying to bring these photons close together, swap the states, and then send photons back. But this only still works in the labs of the universities on very small scale. So that's not applicable yet, but you could sort of compare it with overlay networking as we know it. At the same time, they're trying to come up with, as what we know, an OSI model, where you would have a transport layer, basically physical units sending and receiving qubits, and over that run applications. As I said, there's work in IETF. I have a slide in the back of the presentation with links to some of this work in IETF where that is described. So how does a network then look like? there will, at least currently, always still be a classical network. And with classical, I mean the network as we currently know it. The physicists are referring it to classical. And next to that, there will be a network of quantum links. Again, whether that's satellite links or dark fiber or wavelengths. In this picture, you see sort of combined routers. Currently, no network vendor has equipment to do that yet, but we think in a couple of years, you will see routers and switches that will, next to route IP packets, will also be able to route these photons or create these entanglement swaps. But for now, it's definitely two separate networks. So what can you actually do with this? There are a couple of applications where these quantum aspects could be interesting. For example, if you want to synchronize clocks or telescope baselining, etc., because you can at the same time have exactly the same information in two physically apart places. Obviously, it can also be used, we've already touched on that a little bit, for secure access, sending and receiving keys, for example. There's also already a mobile phone that has a QRNG chip in it. So you see the first applications are happening. The most applicable application currently, and what is also commercially available from vendors like ID Quantique and Toshiba, is boxes that can do quantum key distribution. I forgot to mention, obviously, also maybe one of the most interesting aspects of this is sharing memory and communication between quantum computers once they become available. But let's look at quantum key distribution. First, we'll take a look at how does symmetric key cryptography works. We won't get into all the details, but again, as a baseline, then we'll look at how QKD works, and then we'll try to mix the two together. So as I already mentioned, current security mechanisms and protocols like AES are based on math. So you come up with a very complicated algorithm, and you calculate these keys. And again, as factoring these keys is really hard for x86, we're pretty safe. AES is very safe, as I mentioned. If we come to a point where a classical or a quantum computer can factor these AES algorithm, then we simply double the key size and you're good to go. On the other hand, there is the protocols, the public key cryptography protocols like RSA and Diffie-Hellman, which are very vulnerable to these attacks, as I already mentioned. Basically, public key cryptography is what is vulnerable. Symmetric cryptography is considered quantum safe. The issue there is that you need a way, obviously, to communicate the key you're using in symmetric cryptography between two nodes. And so that is why we consider public key cryptography unsecure and symmetric key cryptography as secure. PQC sort of tries to fill the gap between the two. Now, if we add, as I mentioned, physics, you have an interesting challenge, because with your computers, you cannot calculate physics. So once we start using physics, or in other words, QKD, to transport that key between the two nodes that are using symmetric cryptography, you are considered to be safe. So what we've been working on, and what others are working on as well, is to see how we can use this in MACsec and IPsec, for example, as those are based on AES. So looking at how symmetric key cryptography works, right? You basically have a key source that generates a key using a random source, again, that can be urandom or any other source, and send that key to the other side, where the issue is that both sides know the key and they need to send that key across to the other side. So there is many attack vectors possible. Especially if you would store this data, again, as mentioned, then once a quantum computer is available, you can easily encrypt the data. So if we would start using a quantum random number generator or any other source, and use PQC-based public key cryptography, you obviously still know the key at both sides. So the issue is exactly the same. However, the way you communicate that key is considered to be resistant against attacks from quantum computers using the Shor algorithm we've mentioned at the beginning of the presentation. As considered to be secure because currently there's no proof that there's an algorithm or that could break the encryption. Obviously, over time, nothing is secure, but currently PQC is considered to be quantum secure. But again, there are still ways you can obviously still capture the data. QKD, it might not be the answer from a scalability perspective, but at least it offers a way to securely communicate a key between distant devices, whether it's using fiber or satellite, doesn't matter in this example. Obviously, in the end, the key is still known at both sides, so it's good behavior and advised to have your QKD box and the router that is using those keys, or could be an application, etc., to have those obviously in a secure location. The advantage now is that the key itself is not transmitted over the fiber, as with Diffie-Hellman and even with PQC, you still transmit a key from A to B. In this case, you transmit photons and the key is generated on both sides. We'll look at how that works. And the second thing is, if someone, as we've seen in the introduction, intercepts with the transmission, you will notice because the error rate will rise. So this is considered to be secure against attackers who are after the key. And as we mentioned, the decoherence is still relatively low, so it doesn't help to store any photons or qubits and try to decrypt those later, because you cannot even store them that long. So how does it work? How can we use this? In 1984, two gentlemen, Mr. Bennett and Mr. Bressert, came up with a protocol that uses these quantum properties, as we've discussed, to securely transmit information from one side, Alice, to Bob on the other side. Because it was Bennett and Bressert in '84, the protocol is called BB84. By now, there are other protocols which are variants onto BB84, but the basis is still the same. That's why I'm taking this as an example to explain how it works. So at one side we have Alice, and Alice is sending these polarized photons over a quantum channel. Again, that could be dark fiber or could be free space when using satellites. And on the other side, we have Bob with a photon detector receiving all these photons and reading the polarization state. As you can see, Alice sends, for example, 0 degrees, 45 degrees, 135 degrees, then 45 degrees, etc. Polarized photons. Bob has a photon detector that can measure what the polarization state is. But this would be too easy, right? Because someone could interfere in the quantum channel, reads out the polarization, and then knows if it was a 0 degree or 45 degree polarization that's being sent. So you can retransmit a new photon with that same polarization. So what both Alice and Bob do is they apply a random sequence of filters to these photons. And as you can see, the filter either passes through a 0 or 90 degree polarized photon, or a 45 or 135 degree polarized photon. And because both of them use a random filter sequence, an attacker has no idea which filter to use. And even if you try to filter a 45 degree polarized photon through a 0 or 90 degree polarized or a 0 or 90 degree filter, still some light will obviously pass. So it's really hard to figure out if you're the man in the middle, if you've used the right filter. And so again, if you start filtering these photons and you try to put the same photon with the same polarization on the fiber again and send it to Bob, that won't work because you don't know the random filter sequence, so you won't even know what is being measured in the end. So now if you again measure that, you will see that photons that have a polarization that matches the filter, they will pass. Photons that will be pushed through the filter but have a polarization that doesn't match will give a completely random outcome. If you look, for example, on Alice's side, the first photon will pass the filter. The second photon doesn't match with the filter. So the outcome is, what is it, 200 or 180 plus 45, 225 degrees. So you'll see that the outcome will then be completely random. Same on Bob's side. Bob obviously didn't know which filters Alice has used at that time. So Bob applies a random filter sequence as well. And then as you can see, some photons will pass the filter correctly and some will give random outcome. Now, after that happened, Alice and Bob exchanged their filters using a QUBIT random public available data channel, because if you're able to fetch the photons or fetch the filter, you can still cannot do anything with it. And now if both sides apply both filters, you see that some photons have passed both filters, some did not pass Alice's filter, and some have not passed Bob's filter, or some even didn't pass both. So some measurements will be correct, some incorrect. In the end, it's around 50% of the measurements will be correct by applying this. And that is coming back to what I've said earlier, that if someone would be interfering and would be trying to measure these photons as well and put what he thinks the same polarized photons on the fiber again, then that error rate will increase significantly. So then you know that someone is listening into the conversation. So now if you sift through the results, you see that the photons that have passed the filters have either a 0 or 1. As we mentioned earlier, Bob will measure the same or get the same result on the photon, because if you measure one side, the other side has the same. And the key result is in this case that both sides now have a shared key that is 0101. This is in very quickly how this protocol works and how you can securely transport a key between two nodes. On many slides, I've put links. If you're interested, please click on the links, and there's probably a much better explanation in this case on YouTube of how this works. But again, to give you an idea how you can transport a key from one side to the other. Now, if you obviously we want to do something practical with this. As I mentioned, we would want to use this in IPsec or MACsec. So what you basically do is next to your router, you put two boxes, two QKD devices. You need a dedicated channel for the quantum communication, again, dark fiber or free space or a wavelength. You need a data channel, but that can simply be over the internet. And obviously you need something you want to decrypt. So that is your connection that was already in place between your two routers or two firewalls. How that looks like in a lab environment. In this case, we did a test with a tier 1 provider, where we have two firewalls, as you can see, with a MACsec encrypted connection in between them. A 10G connection in this case, doesn't matter, can be 1 or 100 as well. And there's two, on the right side, two QKD devices. The QKD devices are connected in between each other with the yellow fiber. So that is the dedicated channel. And both have a connection to the, in this case, firewall to fetch the keys from. So let's see how then our routers or switches can get those keys or fetch those keys from the QKD device and actually use them. As I said, both Alice and Bob need a QKD device. Both also obviously need a router. And you need 3 connections in between, right? The quantum channel, the data channel for the QKD boxes to exchange those filters and perform some other synchronization tasks. And between the routers, there is a 110, 100, 400G channel, whatever, protected with MACsec or IPsec. That's just your data channel as you currently know it. Now, the extension to the protocol is that obviously you would need to start fetching those keys from a third party or an external source. And the way to do that is defined by ETSI. So that's why we refer to it as the ETSI protocol. And how that works is the router initiates a API call to the QKD device. That's simply an IP connection. So it basically asks, hey, give me a key. It gets a key back and a key ID. That key ID is then communicated to the other router. Again, that could be simply plain internet or whatever, doesn't matter. With the key ID itself, you cannot do much as long as you don't have access to the QKD devices. So the router on the right side receives the key ID, uses that key ID to request the key from the QKD device. If all worked well, he receives the same key as on Alice's side, and that key then is used in MACsec or IPsec. It could be anything else as well, right? Anything that uses keys can use keys that are generated by QKD. What is standardized currently is the ETSI protocol, so the way how to fetch the keys from the QKD devices. What is not standardized yet is, for example, how to communicate key IDs from one side to the other, how to exactly use that in MACsec or IPsec, how often to roll over the key, etc. So there's still quite some work in the standards organizations there to do as well. As I mentioned, key is made available using the ETSI REST API. Here's a link to the standard. If you're interested, you can read how that works. There is also QKD or virtualized QKD applications available. So you can test against those. Obviously, it is then not secure because it's a simulator that runs in the cloud. But at least you can start testing and playing around with it. And as I said, the key can basically be used in any symmetric key algorithm or protocol. So MACsec, IPsec, but it could also be TCP/AO, for example, that allows for dynamic and non-intrusive key rollover. So how can you use this? And this is where I can definitely use your input as well. So this is just something I came up with. The simplest offer could be to basically just offer direct connections between two customers, right? So next to their connection to your peering platform, either a dark fiber, many IXPs are already offering these kind of services, dark fiber, or a wavelength, for example. So in this case, you can connect, for example, a financial institute to a bank. They can exchange keys in a secure manner, and then connect or transport the data itself over the peering platform, but using these keys generated by QKD. The downside obviously is that, again, the maximum distance is somewhere in between 120, 140 kilometers, depending on which QKD solution you're using and how many patches are in the path. So this is what I've called the passive QKD offer. What could be more interesting is the active QKD offer, where you as an inter-exchange would be sort of a trusted node in the middle, where you would have a QKD device that generates and sends the photons, and two or three or more either customers or one customer and enterprise with multiple locations would have these photon detectors on their locations. So you basically host Alice, and you build a point to multi-point, so to multiple Bobs, point-to-point QKD connections. There are some vendors who offer this also in a solution that would work in a CWDM and DWDM environment, or in different words, it works on different wavelengths. So still obviously doesn't work in a amplified environment, but in this case, two parties could be 2 times 120 kilometers away if you would be right in the middle. I have no idea if this is, for example, commercially interesting. I've had quite some conversations with telcos, with financials, with government, semi-government, who would be interested in QKD to secure their data. So this could be an option for you to play a role in that field. Again, distance is definitely a limitation, and in this active QKD scenario, you would want to be the man in the middle. So I see there is a question in the chat. What is the interface between SRX and QKD device shown previously? If you can please share this information. Yeah, sure. Great question. So the interface is basically just, it's a REST API. So you make from the SRX in this case, but again, that could be a server, could be a firewall or router. You simply make a API call. So it's just an IP connection between the two. So in theory, you could have one QKD device serving your whole network. Obviously, the connection between the QKD device and the consumer isn't that secure, right? So that would preferably need to be in the same location. But yeah, so in this scenario, let's say you have two parties that peer with each other. They could use the keys from their QKD devices to use IPsec, for example, over or on the data they're sending in between each other. But you could also start offering those keys to use in TCP/AO, for example, and offer a dynamic key rollover. So you can leverage the keys. These boxes just keep on generating keys, right? They generate, I don't know, 10 keys per second or something. So you can just ask keys whenever you need them and buy any consumer that needs them. So those are two ideas I've came up with, and I would be really interested in exploring those and see and hear from you if they are of interest and something maybe to do a POC with. As I mentioned, we're working with a few of these QKD vendors, In the picture, you can see the boxes from ID Quantique, but we've also did POCs with other QKD vendors. So we can we don't have production code yet for our equipment, but there is beta code and there's some scripts we can use to fetch those keys and use them in IPsec and MACsec. But obviously we're not there yet, right? There's, as you might think by now, there's quite a few challenges, especially the 120 kilometers is a challenge. So I know, for example, from the physicists at the university here in Delft in the Netherlands, that they're working on these quantum repeaters and entanglement swaps, etc., to overcome that distance. There's also companies working on distributing keys to locations where you don't have QKD boxes. The question then a little bit is it then still so secure? Because obviously you lose part of the security aspects of the quantum properties, but there are still ways where you could use at least the randomness from quantum to generate those keys. And it's more sort of an overlay solution of distributing keys for example, for remote offices or home workers. Multi-point QKD, as I mentioned in the previous slide, multi-point as it is currently is still point-to-point, right? So you have one sender that sends photons to many receivers, so to many bobs, but it's still not really multi-point, right? If you want to go from Bob to Charlie, you will always need to go via Alice. So it's not that multi-point yet. But also a way and something the physicists are now making progress in is to entangle more than 2 photons, right? So instead of having 2 photons with a relationship, they're trying to entangle 3 photons. So if you measure one, the other 2 will give exactly the same outcome. And some of the things we're interested in and what we also would like to hear your ideas is how can we leverage these keys and in what security protocols and what routing protocols should we look into integrating this into the optics or into the boxes, etc. So there's still quite a journey to go. If you're interested in the subject, there's quite a few links on the slides. Here's some additional resources for you to read on. There's many resources on arXiv from more side of university and education, where the physicists are working on their ideas, how they think a networking stack for quantum internet should look like. And there's work in the quantum internet research group in IRTF, in so the research part of IETF, that gives an idea on what their thinking is of the directions. And yes, as I said, the links on the slides are, I think we will share the slides. So else feel free to contact me and I can share the slides with you. So if there's any questions, feel free to chime in if you have suggestions, ideas on if it's applicable, if it's of interest to you. Let me know now, or feel free to reach out, send me an email, and we can chat offline.
So thank you, Melchior, for the presentation. I find the topic very interesting, and it did help me personally a lot to get an overall glimpse of the technology and what's behind it, and very nice use cases you pointed out in the IXP universe. Just a quick question from my side. Of course, if there are any, we can have raise hands and express them in the chat as well. So do you expect that the quantum computers would be, let's say, commercially available anytime soon? Or, and when they do so, do you think that they will pose a serious risk for the current security mechanisms?
Yeah, interesting question. We will see commercially available quantum computers at one point. The question is when. Probably it'll be at least 5 years out from now. So the first steps are there so the physicists are getting better in making it work at room temperature, but they're not there yet. But yes, we will see not a separate quantum computer, but it will probably always be a co-processor next to x86, because there's many tasks that a quantum computer cannot do. But once available, and you have enough capacity to store enough qubits, then definitely there is a challenge for current security protocols. And the question is, how long indeed will it take? If it's 20 years from now, then the question is, how relevant is this what we're talking about now? Because how relevant is your data then, right? Or is the data you produce now, is it still that relevant then? But yeah, so at least I think we're at least 5 to 10 years out before commercial available quantum computers are here.
Nice, thanks. Any other questions?
We have a very silent audience today. Everyone is asleep, probably.
They are trying to digest the topic. It's too much information to be digested in a short period of time, but I'm quite sure that some of the audience will reach out back to you in another forum or in a private email for more questions.
Yeah, definitely. Yeah.
Okay. In that case, I would like to thank you all for coming here and watch the presentation, a very interesting presentation and very insightful by Mel here. And hopefully we will, okay, one more question from Stefan. It's okay. Which kind of business case and what kind of pricing you expect is the question.
Yeah, so for QKD, as I mentioned, business case, currently the interest is primarily from financials, banks, but also trading companies. Obviously, the trading folks are always very aware of who's interested in what they're doing. From a pricing perspective, obviously we don't sell QKD solutions, so I'm not 100% sure, but think about a ballpark range for a single QKD device between 50 and 100,000 euros. So if you want to have end-to-end QKD, it's somewhere in between 100 and a 200K euro probably.
And one more question from Martin Atkinson. He's wondering whether the process of any transceiver and signal regeneration in the signal path will destroy the quantum state of transmitted photons.
Yeah, absolutely. Yeah, and that is why it is so secure, because you cannot tamper or interfere with a photon that's being sent from Alice to Bob in any way. So that's why I'm saying you cannot amplify the signal, for example. So that is definitely an advantage in security, because as soon as you try to do anything with a polarized photon, the quantum state collapses. But the downside, again, is that you are limited by this distance you can span currently. So yeah, so that's Martin. That's definitely one of the biggest challenges we currently have, how to overcome that limitation.
Yeah, and as Zenon mentioned, single photon sources are typically used for QKD.
Yeah, yeah, correct. Yeah. Thanks for adding that.
Any other questions? No. So in that case, thank you, Melchior. Thank you all for being here. Have a wonderful evening, and hope to see you in person soon enough. So
thanks for having me, and thanks for hosting me, Gales. See you all. Bye-bye.
Bye-bye.